Have you ever just stopped and wondered how our modern world, well, works? I mean, everything from the fuel in your car to the plastics in your phone, it all starts in these massive, ridiculously complex industrial plants. But what keeps these giants from spiraling into total chaos? Well, it turns out there's this invisible science, you could call it, that holds it all together. It's called plant-wide process control, and understanding it, wow, it reveals a pretty big secret about how all complex systems really work.
Just look at this. I mean, this isn't a factory. It's basically a city made of machines. You've got thousands of interconnected pipes, reactors, and towers, and they all have to work together in perfect harmony. The scale is just immense. And every single little piece, down to the smallest valve, plays an absolutely critical role. And that really brings us to the big question, right? How on earth do you control something this complicated? How do you stop one tiny problem in some forgotten corner from just cascading and bringing the whole operation crashing down?
Now, at first glance, you might think the answer is pretty simple. You just, look at the blueprint, the map of the whole process.
So what you're looking at here is a process flow sheet. This one is for making benzene, which is a super important chemical that's in everything from plastics to nylon. We're going to use this as our example because it's a pretty standard setup. And when you first look at it, yeah, it seems logical, pretty straightforward, kind of like a city's water map. And yeah, if we break it down, it looks simple enough. You've got your raw materials, in this case toluene and hydrogen gas, going in one end. They go into a reactor, they get separated out, and then, poof, the final product, benzene, comes out the other end. Easy, right? On paper, it's just a classic assembly line. Things go in, things come out. A nice, clean, linear process. But that simple little diagram is hiding a really dangerous secret. Because in the real world, the plant, it kind of fights back. It doesn't always play by the simple rules we draw on paper, and that is where everything gets so much more interesting and so much more complicated. You see, the process itself almost has a life of its own. It has these hidden dynamics, these complex behaviors that our nice, neat little map just completely fails to show. And that hidden behavior? That's where the real trouble is lurking. Okay, look closer at the diagram again. Once we highlight these hidden paths, these lines right here, you see it's not a straight line at all, is it? There are these loops that are sending material backwards. This is where that simple map completely falls apart and all the problems begin. So these are what we call recycle streams. See, to save money and cut down on waste, any raw materials that don't react the first time get captured and sent right back to the beginning for another shot. From a business standpoint, you absolutely have to do this. But from a control standpoint, oh, it is a giant headache. Because these loops create something really dangerous called the snowball effect. A tiny, tiny hiccup, maybe a slight change in temperature or pressure, it doesn't just pass through the system and go away. Nope. It gets recycled, it comes back around, but a little bit bigger. Then it gets recycled again, and it's even bigger. And it keeps growing and growing until that tiny little disturbance can throw the entire plant completely out of control. Listen to how the authors of our source material put it, because it's perfect. They say that you can create what looks like a great control plan for just one single reactor, but the second you connect it to everything else with these recycle streams, your perfect solution could actually make the entire plant impossible to operate. So, okay, if controlling the individual parts is not the answer and can actually make things worse, then what do? Well, it takes a complete shift in how you think about the problem. You have to stop looking at the little pieces and start thinking like a system. See, the old way of doing things was called unit operations. You'd have engineers who would perfect the controls for the reactor, and then another team would perfect the controls for the separation column. Everybody worked in their own little silo. The new way, plant-wide control, starts with a totally different idea. You cannot control any single part without thinking about how it affects everything else it's connected to.
And this is the really crucial point to get. Plant-wide control isn't just about, better computers or some fancy new algorithm. It's a philosophy. It's a whole new way of seeing the plant, not as a collection of separate machines, but as a single, living, interconnected organism. This way of thinking forces you to manage the whole web at once. You have to think about that material snowballing through the recycle loops. You have to consider how energy is shared between different units. You have to track the inventory of every single chemical in the whole system. You just can't tweak one thing without affecting everything else.
And that brings us to what is, frankly, the most profound insight in this entire field. If you really want to control a complex system like this, where do you actually have to start?
Here it is. This one quote is the whole ballgame. The actual physical design of the plant, the size of the pipes, where you put the tanks, the basic layout, that has a much, much bigger impact on how stable the plant will be than any fancy control system you try to slap on top of it later.
In other words, you can't just design a process on a computer to be super efficient and then turn to a control engineer and say, okay, now make it work. The ability for that plant to run smoothly and handle problems is literally baked into its bones right from the design phase, before the first piece of steel is even ordered.
So the huge takeaway is this: these jobs can't be separate anymore. To really crack these problems, the control engineers and the process design engineers have to be working together from day one. To build a plant that you can actually control, you have to be thinking about control before a single pipe is ever laid.
Which kind of leaves us with one last big thought, doesn't it? This whole idea of systems thinking goes way beyond chemical plants. You think about ecosystems, or financial markets, or even the internet. What other incredibly complex systems in our world only manage to function because we finally learned to step back and see the entire interconnected forest and not just the individual trees?